Hello guys, welcome to Physics Grad. In this video we are going to look at something known as the Routhian of a mechanical system, okay, and how it is derived. So let us begin. So in our previous lectures we had found the Hamiltonian of the system by taking the Legendre transform of the Lagrangian with respect to all the generalized velocities. Okay, why did we do this? We did this in order to make our problem more convenient to solve and sometimes to get hold of symmetries that are visible only in the Hamiltonian description. This was the reason why we have to sometimes go to the Hamiltonian description rather than using the Lagrangian description. Okay, and we also know from our lectures in the maths playlist, lecture 9 in particular, that a function of n variables can be equally represented or well described by 2 to the power n functions which are derived using the Legendre transformations on the original function. Okay, so sometimes it may not be convenient, or converting the problem from the Lagrangian formulation to the Hamiltonian formulation may not always be the most may not always be the ideal case where it will make the problem more convenient to solve. Sometimes it becomes useful to take the Legendre transform only with respect to only some of these generalized velocities rather than taking the Legendre transform with respect to all of the QIs. So when we do that, we end up with what is known as the Routhian instead of the Hamiltonian. Okay, so the Routhian is something similar to how we get the Hamiltonian, but the only difference is that instead of applying the Legendre transform to all the QIs, we apply the Legendre transform only for some of the QIs, depending on what will make what is going to become more convenient to us. Okay, so this implies sometimes it is more convenient to take the Legendre transform of the Lagrangian with respect to only some of the QIs, okay, QI dots, and not all. Okay, so we are going to take the Legendre transform for only some of these QI dots, but not all. Okay, the function resulting from such a transformation, the function resulting from such a transformation is called the Routhian of the system. By the end of the video, we will see why sometimes we will have to use the Routhian instead of the Hamiltonian or the Lagrangian formalism. Okay, and the short answer is that it makes the computational task faster. Okay, especially when you have a large number of variables to keep track of. Okay, so to understand this, let us consider an example, okay, where our degree of freedom is equal to 2. Okay, so this implies we can represent or describe the system by using just two generalized coordinates which are independent. So let q and xi denote the two generalized coordinates. Okay, generalized coordinates. Then the variables q dot and xi dot will represent the two generalized velocities. Okay, then our Lagrangian, as we know, is a function of coordinates, velocities and time. So this will be a function of q dot, xi dot and t. Okay, And our Hamiltonian, as we know, we get it by taking the Legendre transform of L with respect to q dot and xi dot, and this will be a function of q, p, xi, eta and t, where p is dou L by dou q dot and eta is dou L by dou zeta dot, that is the generalized momenta corresponding to q dot and xi dot. Okay, so this is what we have studied so far. But now what I'm going to do is I'm going to take the Legendre transform only with respect to q dot. Okay, so take Legendre transform only with respect to q dot. Then it will result in a function which I'm going to call it as r, which depends on q, the conjugate variable of q, which is the generalized momenta p, and since I'm not taking the Legendre transform with respect to xi, the dependence on these will remain as it is, and this is the function that we will get, that is the function which depends on p and q, xi dot and t. Okay, now notice the difference between this and this. So here we have eta also, whereas here we do not have eta. Okay, so that means we have taken the Legendre transform only with respect to q dot and not zeta dot, xi dot. Okay, so that is the difference between the Routhian and the Hamiltonian. Okay, so similar to how we derived our Hamilton's equations, let us try to derive the equations of or the set of equations from which we can get the equations of motion from the Routhian function. Okay, so for that let us first calculate what is the differential of the Lagrangian. So this will be dl equal to dou L by dou q into dq plus dou L by dou q dot into dq dot plus dou L by dou xi into d xi plus dou L by dou xi dot into d xi dot plus dou L by dou t into dt. Okay, but this is nothing but this, as we know, is going to be equal to p dot times dq plus this is going to be p dq dot plus I'm going to leave this as it is, dou L by dou xi d xi plus dou L by dou xi dot d xi dot plus dou L by dou t dt. All right. Okay. So this is going to be what? Okay, so before going there, let us see how to calculate our r. So r, which is a function of q, p, xi dot and t, is nothing but the Legendre transform with respect to q dot. So this should have the form p q dot minus L, where I have maximized the, we know how to find the Legendre transform. We have to maximize a function p q dot dash minus L of q dot dash and so on, and the maximum value occurs at the value of q dot such that our p becomes equal to dou L by dou q dot. Okay, so that is how we take the Legendre transform. If you do not know, please refer the videos from the maths playlist. Okay, and our Hamiltonian was defined as qp xi eta t as pq dot plus eta xi dot minus L. Okay, so this is just to see the difference between how to get the Routhian and the Hamiltonian. Now we already found out the differential of the Lagrangian. Let us now find the differential of our Routhian. So this is nothing but dou r by dou p into dp plus dou r by dou q into dq plus dou r by dou t into dt plus dou r by dou xi into d xi plus dou r by dou xi dot into d xi dot. Okay. Now what will this be equal to? Okay. So here we are going to use this particular relation for the Routhian and calculate the dr as dp times q dot plus p times dq dot minus dl. Okay. So what will this result in? This will give us q dot times dp plus p times dq dot minus whatever is there for our the Lagrangian differential, that is these things we'll have to put it here. So first term p dot dq, so minus p dot dq minus p dq dot minus dou l by dou zeta dou xi minus dou l by dou xi dot d xi dot minus dou l by dou t dt. Okay. So here if you notice this term will get cancelled with this term and what we will be left with is these terms. And now I am going to compare these with this expression and we will see that we have q dot equal to dou r by dou p and minus p dot equal to dou r by dou q. Okay. And rest of the relations say that dou r by dou t equal to minus dou l by dou t, dou r by dou xi equal to minus dou l by dou xi and dou r by dou xi dot equal to minus dou l by dou xi dot. Okay. And if we see our Euler-Lagrange equation, so Euler-Lagrange equation for xi, we will have d by dt of dou l by dou xi dot is equal to dou l by dou xi. Now using the these two relationships, we are going to get the equation d by dt dou r by dou xi dot equal to dou r by dou xi. Okay. So we have this equation and along with the equation q dot equal to dou r by dou p and minus p dot equal to dou r by dou q. Okay. So now if you see that this part has the form of the Hamilton's equation and this part has the form of the Euler-Lagrange equation. Okay. So to get the equations of motion, we have to solve these two equations using our Routhian. So our Hamilton's equations, how do they look? So if we consider the Hamilton's equation for q dot and p dot, they would look like this. Q dot is equal to dou h by dou p and minus p dot equal to dou h by dou q. Okay. And if we had considered the Euler-Lagrange equation for xi and xi dot, then they would look like this: d by dt dou l by dou xi dot equal to dou l by dou xi. Okay. What does this imply? So comparing, so let me call this 1, 2, 3 and 4. Okay. So we see that comparing 2 and 3, R acts like the Hamiltonian with respect to Q. Okay. And comparing 1 and 4, we see that R acts like the Lagrangian with respect to xi. Okay, so this is the important distinction between the Routhian and the Lagrangian. Okay, so it acts like a Lagrangian for some set of variables and it acts like the Hamiltonian for the other set. Okay, so using this, how would we express our energy? So we already know that the energy in Lagrangian formulation is given by summation over I, the generalized momenta times qi dot minus L. Okay, and this is also the definition of our Hamiltonian. So what is the value of the energy in terms of the Routhian? So to express that in our example, we know that this is equal to pq dot plus dou L by dou xi into xi dot, dou L by dou xi dot into xi dot, okay, minus L. But this part is nothing but our Routhian, okay, and dou L by dou xi dot is minus dou R by dou xi dot, as we have already seen. So this becomes R minus dou R by dou xi dot into xi dot. Okay, so this becomes our expression for energy in terms of the Routhian, right? Okay, so in similar fashion, so similarly similarly we can define the Routhian for functions with several coordinates. Okay, so similarly we can define R for L of many coordinates, that is, here we consider just 2 coordinates, but we can have any value for S, and the Routhian with respect to the respective variables will be defined in the same way as how we did for 2 variables case. Okay, so that should be straightforward if you have understood what we did for the 2 variable case. Okay, now the big question is, when does our Routhian become useful? So for this, let us consider, we will take the same example and let us consider the case when dou L by dou Q is equal to 0. This implies that L is not explicitly dependent on Q. So this condition is also expressed as saying that L is cyclic in Q. Okay, so when L is cyclic in any variable, it means that this particular condition is satisfied with respect to that variable. Okay, so in such a case, okay, if we use the Lagrangian formalism, if we use L, then to calculate the equations of motion we have to solve the Euler-Lagrange equations, which say that d by dt of dou L by dou Q dot is equal to dou L by dou Q, and this is equal to 0 because of this. So we have to solve this equation, which I am going to call it as 1, or since I already named some other equations as 1, I am going to call it as equation number 5, and d by dt dou L by dou xi dot equal to dou L by dou xi. Okay, so this I am going to call it as equation number 6, and if we had used only our Hamiltonian representation, then we will have to solve this equation: q dot equal to dou h by dou p, p dot equal to minus dou h by dou q, which in our case is going to be 0, xi equal to dou h by dou eta, and eta dot equal to, sorry, xi dot equal to dou h by dou eta, and eta dot equal to minus dou h by dou xi. Okay, so these two equations together I'm going to call it as equation 7 and this equation 8. Now computationally speaking, okay, computationally we find that when dou L by dou Q equal to 0, okay, the equation 6, okay, is easier to solve than 1, okay, sorry, 5. So you can refer to those equations, and equation 6, sorry, so what did we have here? Our equation will be, so this equation is 7, so I'm sorry, so equation 7 is easier to solve than equation 5, and equation 6 is easier to solve than 8. Okay, what this means is that if we observe these equations, okay, here since this is equal to 0, we have this particular relation. Now to solve this for Q dot, the number of steps required is more as compared to solving for Q dot using this. Okay, so a computer will take more number of steps to solve using this compared to this. That is the meaning. Okay, and this is anyway 0, so we just consider it as a constant which will be equal to the initial condition. Okay, initially what was P, it will remain the same value throughout the motion. So there is no computation involved over there. So what computation we need here can be solved much easily by just fewer steps in this case. So that is the reason why I am telling computationally 7 is easier to solve as compared to 5. And in similar way, if we want to calculate this, we have to first calculate h, that is take h, and that involves more number of steps because now we have to write it in terms of eta. Okay, whereas here we can directly calculate our equation of motion by using just one equation here, where we don't have to express our L in terms of other variables and so on. So when dou L by dou zeta is not equal to 0, this step will become more easier to solve computationally as compared to this step, because this takes additional time to transform our L into this h. Okay, so what do we do? So to make the computations faster, we should make sure that we solve the equations for Q dot of t and Q of t using 7 and solve for xi dot and xi using 6. Okay, and this, as you would have already guessed, can be done using the Routhian by taking the Legendre transform only with respect to Q dot. Okay, so here we have, so this implies using R by Legendre transform with respect to Q dot is going to make the problem easy to solve computationally, and this becomes very important when you are dealing with especially fluid dynamics, where the number of variables are going to be huge, and if we find due to some kind of a symmetry that the Lagrangian is cyclic with respect to some coordinates, then our computation can be made faster by using the Routhian, where we take the Legendre transform with respect to those coordinates which is cyclic with respect to which is cyclic. Okay, so that is the advantage and the use of using Routhian over the Lagrangian or the Hamiltonian description. Okay, so the final moral of the story is that using the Routhian is useful when we are dealing with computationally heavy problems. Okay, so thank you for watching. See you next time.